Up to this point in chemical engineering, most of the time we've been assuming that the system can reach a steady state, and we typically design for that steady state. And quite often we solve those equations as if there is this one steady state which is attainable. And in fact, that's a drastically simplified view of the way these units behave. So in a reactor, for instance, we have a complex interplay between temperature and conversion, and this may well make it difficult to identify which steady state will exist and occur in the reactor, because there may be more than one steady state available. It may also be the case that there's no steady state available. And so in contrast to the developments in the earlier coursework in the degree, we are now concerned about the presence of the steady state. And to illustrate this, let's switch over here and let's think about our differential equations in general. So we've been talking about a batch, a PFR, and a CSTR reactor. So for now, let's think about the batch case, and we have some state variable. So in our batch reactor, we have a temperature and we have a conversion. So we can accept those as states that characterize the performance of that reactor. And in that batch reactor, we have some rate of change of those states. So we have a model that reflects that. And to start considering these possibilities of steady states, let's go back to one of the simpler models that we've been working with. So if you take a simple example from physics, if you have an oscillating spring, you will have found that the model that describes the spring is this. So in an oscillating spring, we can imagine a spring at rest, and then if we stretch that spring by an amount x, then we are introducing tension into that spring. And then if we let the spring go, then the spring will tend to act in the opposite direction to the amount we stretched it out to. So there will be a force, and so I'm writing here d2x dt squared. So x is the distance, and then the second derivative, this is like an acceleration. So we know acceleration is proportional to the force. So the force in the spring, or the tension in the spring, is proportional to the degree to which we have stretched that spring out. And then as the spring travels back to its rest state, right, when you stretch the spring, we expect the spring to, if we release it, then the spring will spring back to its original length. But as it does so, there may be some friction that the spring experiences. So we'll add this term to account for the friction. So this fully describes a damped spring that might oscillate. And to solve this equation, let's first decompose this. Let's get rid of the second order derivative here. And of course, the easiest way to do that is to define two variables. And the first one is trivial. It's x1 is x. And the second one is x2 is defined to be dx dt. So if you think of it then, dx dt we can rewrite as dx1 dt. So dx1 dt equals x2, so that's one equation. And then if you look at the equation describing the physical system, we can write d2x dt as dx2 dt, right? x2 is dx dt. So ddt of x2 is going to be d2x dt squared. So we can write, we can replace d2x dt squared by ddt of x2. And so that takes care of that term, and then we leave the rest the same. This we can see is minus kx1, so minus kx1. And then here we've got minus m x2, right? So this is a fair way to translate one second order ODE into two first order ODEs. And now that we have first order ODEs, we can go and solve it in Python or your choice, whatever language you want to work in. So the idea is we have two variables, and it just so happens I'm calling them y1 and y2 in this case. So we'll put in the oscillating spring just now. Let's just consider this simple case to begin with. So let's say y1 was minus dy1 dt was minus y1 minus 5, and y2 minus 2 minus of that. That's the other one. So we can go ahead and solve this equation. So you can see here I'm just defining the differential equation and then using the ODE integrator. And then number one, we'll just plot t versus y. So we'll see how y1 and y2 are behaving. So let's look at that first. And before we run it, just looking here, we can anticipate that there exists a steady state for y1, which is 5, and a steady state for y2 of 2. So if we run this, you can see here, here we are plotting y1 and y2. So the blue one is y1, and you can see the blue one, we used initial values of 0, looks like. So y1 runs off to 5 and y2 runs off to 2, and so they reach the steady states that we expect them to. And in fact, we might want to think about reducing the time scale. So let's just make this 0. So you can see the two are increasing over time, and they are progressing towards their steady state. Let's increase this let's just make this a 5 here. Right, so you can see those two reach their steady states. So now let's put in the problem that we've just outlined. So our vibrating spring problem. You can see here we said it's minus kx, so that's y1, and then minus m y2. Right, so that's our spring problem. And let's use a nice high value for the damping coefficient. So let's say there's lots of friction in the system. So if we run this, and let's just increase the time scale again. Let's put this back to 3. And you can see here that you had start out with the spring stretched out to 1, and then the spring is moving back to its rest state where there's no stretching, so it's going back to the 0. And I just want to extend this a bit further. I believe I had this on a 1 here. So you can see that that's going down to a rest state of 1. So the system was stretched out, and then you let it go back, and then there was lots of friction, but it managed slowly to find its way back. Now let's start reducing the amount of friction. So K2, remember that's the friction term, so we are dropping K2, and let's run that. And now you can see something strange has happened here. So number one, the spring is going back to the rest state much faster, right? So in the previous case where we had quite a lot of friction, it took a longish time to get back to 0. Now it's going back to its rest state very quickly, but we can see it actually overshot here. Right, so if there's enough tension in the spring, or if it is, well, it's not about the tension. It's how much that spring tends to go back to its original state. So if you like, it's the stiffness of the spring. So if it's a very stiff spring, it might tend to overshoot its rest state. So it was stretched, and then it shut back, and it went so far that it actually overextended, and then it went back to its rest state here. Okay, so that's what we can see in that case. And now let's reduce the friction further. Let's go down to 10 to the minus 3 now. So again, this term, that's the friction term. So we are reducing the friction coefficient here. So we are using quite a low coefficient, and if we run this, now we can see the spring is actually oscillating quite a bit around its rest state. So this spring overshot its mark by quite a lot, And then because it overshot the mark and went far past the rest state, then the tension on the other end pushed the spring back out again, and then again we overshot. So it overshot, but it's a damped overshooting, so eventually it does go back to the rest state here. Now that's the case when we have friction. So at each stage of overshooting, it does go past, but it doesn't go back as far as it was originally. So here it was at perfectly at 1. Then when we released it, it went down to a value just shy of -1, and then it came back. And you see, it didn't go all the way back to 1, and that's because we were losing energy due to friction. So let's switch off friction entirely. Now you see it never stops oscillating. So this system never goes back to its original state or its rest state. And so this is an example of a situation that has no steady state. So it is possible in a system for us not to have a steady state. And we can observe that if we plot this slightly better. So you see here, what complicates this picture, in a way it's kind of hard to read this picture because there's so much going on. You've got two variables bouncing up and down. So your two variables, the first one, the position of that spring, and then the second one is the velocity, the speed at which that spring is moving. So an effective way of understanding the dynamics, right? These are the dynamics, right? It's changing in time. So how is the system moving in time? Right? A better way to understand the dynamics of the system is instead to look at a plot of this variable against this variable. So instead of plotting with time, right? So we know it's changing in time, but we would like to understand the system beyond how it evolves with time. We would rather understand how the variables are related to each other. So we would like to understand how is the position related to the velocity. And so we can plot instead y2 as a function of y1. And if you look in the code here, figure 2 is where I'm doing that. So I'm taking the first column that comes back and using that as the x-axis, and then the second column as the y. And when you do that, you see you get this much clearer picture. And if we think about what this is saying, let's say we consider the initial state 1. So your spring started out extended to 1. So that's here. And then at this stage of extension, your spring was at rest, and then you released it, and then straight away that spring started to reduce in its so the spring started to accelerate, so its velocity went up, so it accelerated, and as it accelerated and moved further faster and faster away from the 1, it was moving back in towards the 0. So it accelerates, it gets to the 0 point, but at 0, in this frictionless case, it's overshooting. So it's actually at its highest velocity when it gets to the what's supposed to be the rest state. So the momentum carries the spring back to the other side, all the way across. And then because the tension starts mounting in the spring again, then it goes as far as it can go, and then it actually stops moving at that end point. So the spring has stopped moving there. But then, of course, it's got a tension that's built up in the spring, and then it reverses direction. So you see, on a graph like this, it's rather difficult to figure out what's going on. But if we plot the states as a function of each other, then we can think our way through how that system is behaving. And in fact, let's go back here and just let's put back some friction. So we know in this frictional case, our system dies down to the rest state, and you can see that here now. So we've started with the 1, and you can see our spring was pushing in towards the 0, and then it overshoots, and so it keeps overshooting, but it's spiraling slowly inwards. So the overshoot is getting smaller and smaller, and eventually it's getting closer and closer to the rest state. So this case does have a steady state. So you have a steady state for particular values of the coefficient here. So this introduces the idea that in your differential equations, the number of steady states available to your system is a function of the parameters that govern that equation. And that's what we'll be exploring in the context of our reactors. So of course, in our case, as we said, our variables are not position and velocity, it's conversion and temperature. And so we are interested in the relationship between dx dt and dt dt, or dx dv and dt dv. And you might say, well, clearly you're talking about batch and PFR here. So yes, I did write it that way. However, we should note that it's almost never the case that in industry you have steady state. Your system tends to be bouncing around all the time. So in all these reactor types, quite often things are changing in time. And so we have to be aware that the system is not sitting happily at our desired steady state. The system in industry is always going to tend to bounce around. And so the dynamics of the system may well be a concern to us. Furthermore, in these reactors, we ignored the gradient in space when we used perfect mixing. However, of course, in reality, we never get perfect mixing. In the real world, there may well be differences in temperature and conversion at different points across the reactor. So neither of these can be assumed to be zeros. And so the moment that happens, we have to think about the dynamics of the process and of the system. So here's another example introducing this idea of dynamics. So imagine we have a ball, and here we have a cross-section through our mountain. So we have a hill up here, and then of course we have 2 valleys. And so if we have a ball here, and then let's say we drop the ball at some point here or some point here, we can reasonably expect that ball will roll downhill, and then it may rise up here to some extent, but of course there is friction as it's rolling around here. So it will roll around for a while, and then it will come to rest down here. So that's an example of a stable steady state. And in the example we were looking at here, you can think of this as a stable steady state. You've started out at some value, and the system falls into this steady state, which is stable. And there's a similar stable steady state here. So if you release the ball anywhere around here, it may oscillate around for a while, but it will come to stop here. So that's another stable steady state. So you have 2 stable steady states in this case. On the other hand, you could instead position your ball identically at the top of this hill. So even if it was a perfect curve like shown here, you could find some location, some precise point where if you place the ball perfectly on that point, then the ball has no tendency to fall in either direction. So it will just stay there. So that is a steady state at the top of this hill as well. However, in this case, the moment you have a slight disturbance in the environment of this ball, if there's a slight breeze or just some minor vibration, the smallest thing here will cause that ball to fall in one of these directions. So this is what we call an unstable steady state. These are stable because if we apply a minor disturbance here, the ball may rise for a short while in either direction, but it will be attracted back down to this point. So we call these attractors, right? Steady states are known as attractors. We call them attractors. And then an unstable steady state we call a repulsor. Our system tends to repel us away from this steady state. So you could also think of it as if somehow we were to push towards B, then the system is always fighting against us and always trying to push us back down here. So a system may push us away from one steady state and towards another steady state. And if you can abstract your view of this, and if you can imagine perhaps that this is a desirable steady state, let's say this is a steady state that has a high reaction rate, and this one has a low reaction rate, then knowing that the kinetics are like this, if we know that there's this hill and that we have to supply enough energy to get this ball over this hill, then we'll know that we can enjoy operating at this steady state. Otherwise, we are stuck to this other undesired steady state. So these are the kinds of concerns we are looking at today. So let's apply that now in the case of our CSTR. So of course the material balance of that CSTR applies. We can rewrite it like that. And then if you look at your energy balance, so going back to the energy form of, the form of the balance that contains heat transfer, so Q dot is not zero. So if you go back to your energy balance, you'll find that that's exactly what we derived. And please do that. Please go back and verify that that's our energy balance. So that's a form that we have. And in here, we want to replace this FA naught X part. So we just said from our material balance, we have FA naught X equals RAV. So we can go ahead and substitute FA naught X by RAV over here. So we are doing that because we would like to get rid of this X. We would like to rewrite this equation just in terms of temperature. So we've got RAV and everything else is the same. And then just for the sake of convenience, we go ahead and define this kappa as a UA over FA naught sum theta I CPI. So you can see here, if you group out this factor, if you group this out as a factor, you're going to get UA over sum theta I CPI. And so that's what we do here. We just group out this part. So we take that theta CPI out as a factor. That leaves us with T minus T inlet. And then that gives us here UA over FA naught sum theta I CPI. So we can replace that by the kappa there. So that's kappa, so that's there. And then the left-hand side stays as it was. Okay, and then you can regroup this slightly differently also. So you could group out in terms of temperature. So you've got temperature in both terms here, so you can group out for temperature instead. And it's saying here we recognize the left hand side has this heat of reaction part. So if you look at this, this is the right hand side is in a sense, maybe let's look here. The right hand side has more to do with our supply of heating to the system. So we are feeding the system with the stream with a certain flow ratio, and then we are applying temperature differences across that. So if you like, that's the heating that we are applying to the system. So that's this part. And then on the left hand side, we have the response by the system. So this is the energy, the thermal energy given off due to the reaction. So as the reaction proceeds and reactants become products, then the chemical energy changes. So you might get higher energy products formed, in which case we have to take energy, thermal energy from the surroundings, and so that will change. So this is the response of the system to the reaction happening, and then this is our applied heating and cooling to the system. So if we view it that way, then we can give some names to these terms. So you could think of this as the heat generated by the reaction.
I need your consent. consent on a few.
So here we are writing G of T, meaning the heat generated by the reaction. So of course, energy is not created or destroyed, it's only converted from one form to the other. And in our case, we've got a kind of chemical potential energy being converted to thermal energy. So this G of T is, when we say heat generated, we mean specifically thermal energy that's built up due to reaction here. So that's heat generated. And then, as we said, we are thinking of this as the heat that we are applying. So this is energy removed. We'll call it that. Okay, so we can define G of T and R of T. And now let's think about finding a more specific form for our G of T. So we've said G of T is RAV over FA naught heat of reaction. And of course, if it's in a CSTR, RAV over FA naught, that's nothing but X, so we can replace by X here. Right, and now we would like to replace that X by a temperature function. And to do that, we need to think about the reaction rate, so the reaction expression. So let's assume, just for the sake of a case study, let's assume it's a first order reaction. So now we are looking specifically at the case of a first order reaction. So this is no longer general. So up to now, everything we've said was nice and general. Now we are looking at a first order reaction. So if you have a first order reaction, your RA is KCA. So if we rewrite the material balance for the CSTR, FA naught X over RA, we are replacing RA by KCA. And we know that CA we can replace by CA naught 1 minus X. Then on the numerator we had kept the FA naught X. So we have this ratio now. And we know we can rewrite FA naught, right, that's the molar flow rate. That's equal to the concentration CA naught divided by the volumetric flow rate. So this is CA naught over Q. Or CA naught over Q, and then CA naught can cancel with that CA naught. So the CA naught is gone, and then leaving us with just the Q part there. And let's see, so then we can divide this volume by Q, and remember V over Q is tau. So you'll have tau here, and then if you multiply by K, you'll have tau times K equals X over 1 minus X. And then you can solve that for X and show that's equal to tau times K over 1 plus tau times K. So I haven't shown all the steps here. Just please work through this carefully and verify, ensure that you agree with this. By the way, here I think I said it wrong. FA naught equals CA naught times Q. All right, so here I'm writing it as V naught, but this is a Q. So yeah, FA naught equals CA naught times Q, and the CA naughts cancel, and then you're left with the Q there. And then so you've got Q here. So if you say V over Q and then multiply by the K, then you get what we said. Okay, so we've got X now looking like this, and this is useful because we've got K's in here. Right, this K being, of course, the reaction. We said RA equals KCA. So all we need here is the Arrhenius relationship. All right, K equals K naught e to the minus E over RT. So we use the Arrhenius relationship here, and then that will give us G as a function of T. Everything else is approximately constant, and I'm just going to write it out here. So K equals K naught times X of minus E over RT. Right, so that's your Arrhenius expression that you substitute here, and so X is tau times that K. So you can see it's quite nonlinear in T over there. The heat of reaction we know is generally a temperature function, But if our delta Cp is low enough, then we can think of this as a constant. So it's quite often the case that heat of reaction is only a weak temperature dependence, whereas this one is going to be quite a strong temperature dependence. So this term will dominate, and our temperature dependence is largely a result of this here. Okay, so that's how we can get the heat generated as a function of temperature. Oh, I see it's all done here anyway. Okay, so if you were to plot this out, this is the kind of thing we'll see. So you'll get a curve. So at low temperatures, G of T tends to be low. And you can see here at low temperatures, this is small and this is small. So it's approximately 0/1. And so you'll get a small value here. And then as temperature rises and these two become much larger values, then this number becomes much larger than 1. So it's approximately just this. So just this over just this is approximately 1. So this becomes closer to a saturated 1. And then this number is very similar to our heat of reaction. So as T goes off to infinity, G saturates at the heat of reaction. Right, so that's how you can sketch this out quickly. We know it starts at 0 and it levels out at the heat of reaction value, and then it's just a matter of figuring out or generating some points in between here. And here's a comment that as EA changes, so the activation energy here, that changes the slope of the line. So for high EA, this curve gets sharper and sharper, and for low EA, you can see it flattens out there. Tau is also in here, so tau appears linearly in this term. So you can easily think of how tau influences this as well. So as you increase tau, you get to the sharper responses, but with the same features, 0 and heat of reaction there. Right, so that's the G of T side of it. For heat removal, of course, we go back to this equation. This one is in a sense easier. It's quite linear in T. So kappa, if you go back and have a look, that's nothing but dependent on the constants. These are all constants. T in is of course a constant. That's a constant. So the only variable here is T. So R changes linearly with T. Yeah, so as you vary kappa, then you can see your R of T is responding in this way. Just have a look at kappa. So, yep. So that's how R is changing as a function of kappa. Now let's think about what that means when we draw our system out. So let's remember we got this by taking the original equation. So going back here, we had said we have thermal energy given off and we've got energy being removed. So those two are equal. And actually, those two are equal at steady state, right? If you look back at some of our earlier developments, when we were considering the unsteady state case, then we had something times dt equals this minus that. So anyway, at steady state, these two are equal. And so we can now go and plot those two lines. Right, so if we produce this figure, so we draw our G of T, and then we can draw R of T. So we can consider different initial temperatures. So if we go here, you can see the inlet occurs as just an offset. So we can plot different removal lines. So energy removal lines, we can plot them like this, and we can think about what's going to happen in the system when we do that. So let's take let's just take this line to begin with. Okay, let's not do that. Let's take this one where it says Ti, 3. So you've chosen an inlet temperature that has that value. And now down here, let's look at the numbers. So if you pick a point here on this line, you can see here that your equivalent, your generation term is higher than your cooling term, right? So if we pick this temperature, right, this temperature here, you can see your generation value, your heat generated, is more than your heat removed. So that means, on balance, your temperature is going to rise, right? So once more, when you look at these two lines, right, there are two lines to look at here. One is the heat generated line, the bold line here, and the other line is this this straight line. So this is the heat removed line. And if you are generating more heat, if you are tending to increase the temperature on this line, and if you are tending to reduce the temperature on this line, then the difference between these two will tell us whether on balance the temperature is rising or falling. So here you are tending to increase the temperature more than you are tending to decrease the temperature. So on balance, your temperature will increase. And that means in terms of the temperature variable here, we will move more towards the right. So if we start here, the system will run away to the right. So starting here, that we've got more heat generated. So we will be rising, and then we'll rise and we'll reach this point. And now, if we think about going past this point, if we go to temperatures out here, you can see now the heat removed is more than the heat generated. So beyond this point, your heat removal rate is greater than your heat generation rate. And so if you are removing heat faster than you are generating heat, the temperature will tend to drop and you'll fall back to this point. So that's why we can think of this point 4 as a stable steady state. If we start below the point, we'll fall into the point. If we start above this point, we'll also fall into that same point. And if we are operating on this point, and if, let's say, there was some minor fluctuation, let's say the feed to the reactor suddenly had a small increase in temperature, so it pushed the system there, then the system would still be attracted back to this point. So this is a nice stable steady state down here. It might not be the best operating point, it might not give us a high reaction rate, but it is stable here. That is a stable steady state. So for all values along this line, right, all values up to here, you will have a higher heat removal rate than a heat generation rate, and you will always fall back to that 0.4, right, until you get to 0.5. So at 0.5, the moment you get slightly disturbed below that temperature, you will fall down in this direction and you will fall towards 0.4. The moment you go slightly above 0.5, your heat generation rate will be more than your heat removal rate, and you will fall up to 0.6. So again, this is a repulsor point. It is a steady state, so if you start identically on this point, your heat removal and your heat generation values are the same, so the rates are equal, and so the system won't change in temperature. But the moment there's a slight variation, it's going to run away to one of these other temperatures. Okay, now as your system runs away, you can see again a stable steady state here. So if you go above the temperature here, your removal rate goes higher than your generation rate and you fall back here. If your temperature somehow goes below this, then the system moves so that the heat removal rate is less than the heat generation rate, and it will rise again. So that's a stable steady state. And in fact, all that applies to all these points here. So all these points down here are stable steady states. All these values here are stable steady states also. All these values here are unstable steady states. So those are some features. That's how we can think of navigating this plane. And now there's another special value that could arise. So let's say we liked operating up here because we know the temperature is nice and high here and we get nice high reaction rates here. So our inlet temperatures were all in this range. And then so that's at the inlet point, but in the reactor we are operating in these ranges. And now let's say suddenly, right? Our inlet temperatures are actually over here. So our inlet values are all here. So for all inlet values more than Ti2, you can see these steady states are stable. Now let's say our inlet temperature slightly dropped below Ti2. So if you drop below Ti2, you are no longer along this line. You are suddenly out here. And out here, there isn't available this intersection anymore, right? Before, when we were above Ti2, you see your intersections were always with this branch up here. So we were always falling to one of these steady states up here. But if your inlet temperature, right, so, and here we were talking about temperatures in the reactor. So for inlet temperatures more than or equal to Ti2, our reactor temperature was always stabilizing somewhere in this region. Now, if the inlet temperature slightly drops below Ti2, suddenly you don't have available in the reactor steady states in this region. Suddenly, you only have available this one steady state down here, or steady states to this side. So that means, let's say we were trying to operate the reactor in this region and find there was a bit of fluctuation, but we were moving around here. And then suddenly our inlet temperature dropped just slightly. And now suddenly you find the system will run all the way down to this steady state. And so we think of this, this value as an extinction point. So if we go slightly below this value, the system runs away to this low temperature region. So it extinguishes what we were trying to do in that reactor. So that's an important feature for us to understand, right? We need to understand that our inlet temperature is not some arbitrary number that we can just go and specify. That inlet temperature has to be carefully chosen because the thermodynamics of the system are such that there are specific regions down here which influence our operation and what kind of steady state is available to us. It can totally upset our attempt to control that reactor if we have the wrong operating parameters. So we might stray into an extinction point, we might stray across an extinction point and kill the reaction. And then the reverse can also happen. So let's say we wanted a low temperature. Let's say it was a biochemical reactor where we didn't want to go and fry our poor little bacteria, or let's say it was a polymerization reactor and we didn't want to have a total meltdown in that reactor. So we were operating in these low regions. So we want these steady states. Now you can see here that will all be fine as long as we keep our temperature below our inlet temperature. As long as we keep our inlet temperature below Ti5, we can have these steady states. But the moment our inlet temperature goes slightly above Ti5, suddenly the system doesn't have a steady state down here, and it's going to fly away up here. And so this is going to be what we call an ignition point. So the system ignites. For some reason, the temperature shoots up, and now we are in this high temperature region. And this is what actually happens, right? We'll be talking in the next session about some case studies, and we'll look at where through a slight ignorance about the kinetics and this complex interplay of energy and kinetics, that there were failures of the reactor. And by failures, I mean the reactor exploded. So understanding the influence of kinetics and energy, we take important considerations into account about safe operations of that reactor. So again, we have features, we have steady states, and now we have to distinguish between stable steady states and unstable steady states. And we could transition among the nature of the steady states we have ignition and extinction points. So all these interesting characteristics exist in a dynamics plane, and they are important things to acknowledge and to design around when developing our reactor designs. So that's what we can see if we plot G and R as functions of temperature. Another way of plotting it, you can see how important it is to understand what's happening with respect to the inlet temperature, which is not the same as the reactor temperature. So this is reactor temperature. It's not the same as inlet temperature here. So instead, we could plot this as a function of inlet temperature. So we can say for the lower branch, these are the steady states, and the upper branch, those are the steady states. And then you have that branch of unstable steady states. You can also draw this nice table here and say, for inlet temperature 1, we have just one steady state possible. So that's shown there. T1 is that one available steady state. For inlet temperature 2, we have 2 steady states possible. So one stable steady state and one kind of saddle steady state. So 2 over there. And then for Ti3, you do have 3 possible steady states available. And then it's a matter of where you've started. So your initial temperature in the reactor decides which steady state you are going to fall into, and so on. So you can read this table and see that you agree that we can identify for a particular inlet temperature what steady states are available in the reactor. Okay, so yeah, you can look at that, and so this is now talking all about the plane, and we can go ahead and we can estimate when the system runs away, and so it is important for us to be able to figure out where those features are. So being able to figure out that this ignition point exists down here, and this extinction point exists up here. So we want to be able to find out what this temperature is. So to find this temperature, we have to think of a criterion. So have a look at this. Think about how would you find this point. Maybe pause the video right here and have a think about this. How would you, what criterion would you apply to find these values? So hopefully you've taken some time to think about that, and clearly there's a tangency going on here, right? Your R of t line is a tangent to the G of t line here, and the same here. So if we can find, if we use the properties of tangency, we should be able to find this temperature. And so what are the properties of tangency? Number one, at the point, the gradients are the same. You can see the gradient here and the gradient on this curve. Those gradients are equal. And they're not only the gradients, but the values themselves. So to be a tangent point, you are on the same point. So the, G of t and R of t are the same number as well. So we can use those two together. And so first we can estimate the gradient, so just by differentiating G of t with respect to t. So if you do this differentiation, so of course Ra is the one that's going to have the temperature dependence. So if we assume heat of reaction is only weakly temperature dependent, we regard that as a constant. And so it's just dr dt. And depending on what kinetics you have, you can just substitute your rate expression here. So you would basically end up differentiating your Arrhenius term. So if you differentiate that with respect to temperature, clearly you'll get something like this. So that's your dg dt. So you can substitute that here. And then if you look at that, if you look at the form of this and compare it with G of t, right? G of t is this thing. And you can see this part is just k. So it's k times that function of concentrations. So you can replace this again by R. So you can just rewrite it like that. So that's that part. And then for your heat removal, this obviously is easier. It's simply linear in T. So if you differentiate R with respect to T, it's just going to be 1 plus kappa times this thing. And so you can do that. And if you substitute all that, then you can again say, well, if I look at it, it looks like R of T over T minus TC. So you can read the algebra here, and you can verify that you can represent dr dt in that way. So we are saying the gradients are equal, therefore this equals this. And then we also say that g of t equals r of t. So these two things can cancel, leaving us with this nice relationship. So we can easily solve this equation. It's just a quadratic, and we can find the value of temperature, which gives us the ignition. Well, it's a quadratic, so the solution to this gives us two values. So it's giving us both the ignition and the extinction points. So that's how you can solve it for this case. Okay, so that's how we can identify the important dynamics features in this case. And then on this last page is just a comment that we must start thinking now about multiple reactions participating. So up to now we've taken a very easy view, a single reaction, quite often first order, but now we have to respect that there will be multiple reactions occurring in the reactor. And then if we are looking at a particular component, it's just a matter of adding up the contributions from each of the reactions. If we are talking about the energy, the heat of reaction, then you just have to multiply by the heat of reaction of each reaction multiplied by the reaction rate of each reaction. And so our energy balance then will be a sum over all reaction contributions rather than a single multiplication here. So that's just a small correction that we have to apply to account for multiple reactions. Okay, so that's pretty much it. We respect now that the kinetics actually result in complex dynamics features, and we have to know what features exist in that reactor if we are going to have any hope of operating it and designing it properly.